issue. I've restarted it all, so we can get going. Uh, Good morning. It's great to see loads of you online, and today's session is about covering a bit of C1 energy changes, which Year 10 will have covered back in Year 9, and Year 9 this is something you would have covered at the start of the year. And in today's session, it should take about half an hour, maybe a bit longer. I want to cover several things. The first thing we're going to look at is what are exo and endothermic reactions. We're also going to look at why there are energy changes. Why on earth do we care about energy changes during a reaction? And we're going to move on to looking at how we can draw these out in energy profile diagrams to make it quite easy for us to visualize. And then we're going to move finally on to something called bond energy calculations, which can sometimes be tricky, but we're going to break them down and make them quite straightforward, hopefully. Now, before we begin, just a reminder that in the description of this video you can find a link for some past paper questions which I've uploaded for everybody to download. Go ahead and download those and have them ready. We will be using them later on in this session. Okay. Any issues, any questions, feel free to throw them in the side in the live chat, and I'll do my best to answer them as I go through. But without further ado, let's get going. So the first thing we need to realize is a chemical reaction involves several things. It involves 2 or 3 different processes. And the key things that we look at as chemists is bonding. Now what we say is chemical reactions involve bond breaking. That means we have to break bonds first in order for a reaction to occur. Something which you don't really need to know too much about is that we can form something called intermediates. And these aren't too important right now, but they are chemicals which are formed during a reaction, are also used during a reaction. Next, the final step in chemical reactions is if we're breaking bonds in the reactants, then we have new bonds being formed in the products. And to clarify this a little bit further, bond breaking normally happens in reactants, whereas bond making generally happens in products. And that's a distinction we should be aware of. Of course, all of this involves energy changes. Without energy changing or moving around, there's no reason for bonds to be broken or bonds to be made. And that's what today we're going to focus on. Okay? Before we continue, I think it's important for us to realize that when we are breaking bonds, like with anything, if you want to break a pencil, if you want to break an object, if you want to break a wall down, it's a process that requires energy. So it requires energy, and therefore you need to put in energy. And then slightly non-intuitive, bond making tends to release energy, and that's an important distinction for us to make a note here. Releases energy. Now, often students get quite confused about what's going on with these reactions, and we can summarize them with 2 names, 2 very straightforward names, which can help. And the first one is what we call endo. Endo refers to inside, internal, and it's endothermic, which means taking energy in. Whereas releasing energy is what we call exothermic. Exo meaning outside or outwards. Two different words. You can remember exothermic as exit. Quite a nice little synonym, but exit. Um, exit energy. Now, something which can really help our understanding is to try and visualize this graphically. And I'm going to delve into something called thermodynamics, which you do not need for GCSE, but if you're interested, it's a wonderful branch of chemistry and physics that you will study more of at A level if you continue. And thermodynamics tells us to think of all chemical reactions and, in fact, many other non-chemical systems as a system and the surroundings. The best way for me to kind of demonstrate this to you is the system you can think of as the reaction itself. So if I go ahead and just make a note that this is the reaction, this is the chemical, or these are the chemicals which are undergoing reaction, and the surroundings are everything else. It could be the air, it could be the water that the reactants are dissolved in, it could be everything else. And for an endothermic reaction, if we begin with endo, I might just move everything down so we have a bit more room to play around with. There we go. Obviously, we need to keep things quite clear. So here's my highlighter. There we are. So in this kind of reaction, which is endothermic, energy is going to be, as we said before, moving in to the reaction. The reaction requires energy. So we can very easily represent this with arrows showing energy moving in the system. And when we talk about energy, we're referring to thermal energy, which is moving in. For exothermic, on the other hand, it's the opposite. And if we go ahead and draw our system and our surroundings again, this time we know that the energy is being released by the reaction into the surroundings. And I always found this is a very straightforward way, hopefully, for you to memorize and remember exo and endothermic. And if you can refer back to these diagrams, it makes your life immensely uh, easier. Thermal energy. There we are. Now, it's all well and good drawing these. What we also need to be able to do is describe what is happening. And usually this takes the form of a couple of 2 to 3 mark questions where you need to talk about energy changes. So if we focus on the left, the endothermic, what are the energy changes? Well, we can begin by saying, let's look at the reaction itself, the energy of the reaction. And in brackets, I'm going to make a note, the system. What's happening in terms of thermal energy? Well, if energy is moving in to the system, then overall we're going to have an increase in energy in the system. The second thing you need to look at is the energy of the surroundings. And quite clearly, if energy is moving from the surroundings into the reaction, then overall the surroundings are going to lose energy. It's going to decrease in energy. If we go across to exothermic, you can see that it's actually the opposite. The energy of the reaction is decreasing because it's losing energy, whereas the energy of the surroundings are going to increase. And that's quite a nice, simple system for you to use to memorize this. Now, it does go a little bit further. I want to introduce a term which you've been using since probably primary school, but for some reason it can get quite confusing when we're talking about exo and endothermic. And that term is temperature. Now, I have deliberately drawn temperature outside in the surroundings because what we need to be aware of is temperature is actually a measure of the surroundings. The surrounding. So if I just I'll come back to this in just a moment. Just to give you an example. If you had a beaker of water within which you added in reactant A and B, and we will assume that A and B are going to react. And if you also had a thermometer in this beaker, quite clearly the thermometer measures the energy change of the H2O, the water. And by that logic, it's a measure of the surroundings, or the surrounding, I should say, not the reactant. So using this as an example, if energy is taken away from the surrounding and given to the reaction, that means your thermometer will show a drop in temperature. The temperature will also decrease. Conversely, the temperature, which is out here, again, in an exothermic reaction where your reaction is releasing energy to the surroundings, the temperature will always be an increase. Give me wrong way around. There we are. And I hope so far that makes sense in terms of what is going on in a reaction, what we need to talk about. What I'd like you to do is for the next bit, if you could make a note on your piece of paper, energy, and we'll call it the system, energy of the surroundings, or surround, and then temperature, these 3 points. I'm going to play you a short video of a reaction, and I'd like you to make a note whether there is an increase or a decrease in each of these areas. So does the energy in the system increase or decrease? Does the energy in the surroundings increase or decrease? And what happens to the temperature? And those of you in year 9 will remember this this experiment we did during Science Week. Without further ado, I will play this. I'm just going to enable the sound. And off we go. That wasn't good, so I will rewind and play again. And I'll play that again one more time. Wait. Not getting copyright. So 3. Those of you who saw that live, it was quite a spectacular reaction. It was a reaction of aluminium with silver nitrate. It's a displacement reaction. And in that reaction of aluminium plus silver nitrate, the reaction ended up with silver being produced and aluminium nitrate. We need to balance this, so we'll go ahead and chuck a 3 in front of there, and we'll put 3 in front of AG. And I'm sure you're probably following, but the energy of the system decreased. The reaction gave out immense amounts of energy. The surroundings increased in energy, and the temperature went up. And we could see that. We saw light being given off, heat, an immense amount of heat given off. I remember feeling the reaction. It was, even with the visor on, it was quite warm. So that's the first part, first objective down. Hopefully that helps your understanding, exothermic and endothermic. And I think what we'll do, we'll quickly move on to looking at energy profile diagrams and seeing how we can represent these reactions. Now, I appreciate for some of you, this is quite recent, and you're probably quite well aware of energy, and you're feeling quite confident. But there are some small bits that you can perfect and make sure you don't fall foul of. So, an energy profile diagram, I'll go straight into it. It represents two things. It compares the energy change of a reaction during the course of a reaction, or the progress, I should say. Probably better word is progress. So in English, what is the energy of in the reaction at the start, and what happens during the reaction. Now, importantly, I'm going to make a note here. This is always a measure of the energy of the system, okay, aka the reaction. So this doesn't represent the surroundings. Here we are. So you'll be familiar with this. You've seen this before, where you have your y-axis, you have your x-axis, and I'm going to show you how to draw the perfect energy profile diagram. This can be worth up to 4 marks in an exam paper, so it is worthwhile getting it correct. On the y-axis, we have energy represented, and the units we measure in is kilojoules. If you remember, joules are the SI units of energy. We're doing kilojoules because we're looking at huge amounts, and it's kilojoules per mole. Those of you in year 10 studying the mole, you'll know what we're talking about. Year 9, you have that to look forward to. The x-axis is the progress of the reaction. And what we mean by that is the start and the finish of the reaction. And as you're well aware, we always start a reaction with reactants. Now, it's important to note that the y-axis is an arbitrary scale. You will never need to label up numbers or add on specific scales along here, because it's actually quite difficult to do. So let's go ahead and start with an endothermic reaction. When my iPad behaves. Now your first job is to start anywhere on the left hand side and draw your starting point. Okay, there's my starting point. And I'm going to go ahead and write down reactants underneath. Now, using what you know about endothermic, and you can comment in the live chat, for products in an endothermic reaction, will they have more or less energy or the same as the reactants? The options we have is that the products have the same amount of energy, they have more, or they have less. We'll call them A, B, and C. And again, I've drawn them randomly. What do you think? Okay, we've got a suggestion of more. You know what? Let's move on. Yeah, you're absolutely correct. Endothermic, you're taking in energy, which means overall there is an increase in energy. And we'll go ahead and label that the products. Now, you might not think it, but that's actually worth 1 mark in a lot of exam questions, just for getting that correct. The second bit is to show the energy change from reactants to products. Now, more often than not, students in Key Stage 4 will often draw a straight line to link the two. And that's to show that the energy difference between reactants and products is straightforward. That's actually not the case, and we need to be very careful. That's a misconception. What we need to appreciate is for a reaction to kick off, there needs to be an input of energy for a reaction to start. Reactions usually don't just begin on their own of their own accord. There needs to be an input of energy. And that can be from light, it could be from temperature changes, it could be from kinetic energy, it could be UV light, for example. And these input of energy we call the activation energy. It's always greater, so if we start from the left, it always goes above the products. And the maximum point of this arc is your activation energy. And then you join the products. That is your second mark in an exam for drawing the correct profile. And then your final mark is to correctly label activation energy as well as the energy change of the reaction. And this is something a lot of students can often confuse. And first, when I was your age, I did get baffled at times. Activation energy is defined as the amount of energy needed to start the reaction. And it's the difference between the reactants and the highest point of our profile diagram. Be very careful. Often people get penalized because they will draw the line slightly off the arrow. To be fair, this is still correct because my yellow arrow still reaches the maximum point of the graph. What you need to be very careful of is not to be the person who does this, because that is not the entire activation energy. That is wrong. Okay. Another common mistake is to draw from the products to the maximum point, and so on and so forth. Let's move that back. We can label that EA, which means activation energy. And then finally, the energy change of the reaction is the difference between the reactants and the product. And it's often given a symbol delta H, or energy change. More about delta H in a short while. So far, I hope that makes sense, and it's nothing too new. Hopefully, this is bringing back some memories. And if I just go ahead and move everything down so they're spaced out. The next reaction we're going to look at is exothermic, and this is quite a nice one actually. Exothermic isn't too bad. Similar thing, get your axis up. I'll speed through this because I know a lot of you want to move on to bond energy calculations. Energy, progress of your reaction. Once again, the best way to start is just draw your reactants anywhere. For exothermic, I like to do it slightly higher up so I have room. Now, as it's exothermic and the system is losing energy, this time your products will be lower. And that's 1 mark so far. Again, a common mistake is just to connect the two by drawing a line straight from reactants to products. We have got to take into consideration activation energy once again, and therefore it's slightly different. And it's actually the same as before. So if we go ahead, we need a minimum amount of energy to start the reaction, and then the second half, try and make it a bit neater. There we are. Activation energy is again the energy change from the reactants to the highest point of our profile, which means the energy change of the reaction is a difference between the reactants and the products. So energy change of the reaction. We'll ignore the fact that my battery is low. So far, I hope that's been useful as a recap of energy change theory. And you need to get used to drawing these profile diagrams. The exam pack I've given you in the link in the description at the bottom has many questions which ask you to draw these profile diagrams. The mark scheme is at the back of the question pack. And without further ado, I'm going to move on to the third or fourth part, in fact, bond energy diagrams, which is quite a nice concept once we get into it. So, bond energy calculations. Now, the first thing we need to be aware of is each type of bond has a fixed or a specific value of energy needed to make or break the bond. And I've worded this in a very strange way on purpose because often people think it's to break the bond, but actually it's also bond breaking and bond making. They both work in the same way. And to give an example, I'm going to make the numbers up. So the values will always be given to you. But for example, if I had a CH bond, normally you'll be given a value, and it'll be in kilojoules per mole, which will tell you that it's, let's say, 72 kilojoules per mole. Now, we've already mentioned that if you're breaking bonds, then the value is positive. So I'm going to go ahead and make a note that it's plus 72 when breaking this bond. Because if you remember, you have to put energy in to break a bond. So in this example, we're putting in 72 kilojoules per mole to break the bond. If we were going to make a CH bond, then all we need to do is flip the sign, and it becomes negative. There is a foolproof way of doing this, and it's a formula you will have come across. And what I'll do is I'll work through an example with you as a team, and we can have a go. I'm just going to bring up some questions. Just a moment. Let's move it to the side. So I'm going to basically work from the data sheet that they've given in this table, so I don't have to make it up from scratch. Okay, perfect. So the key equation for you is this: you need to, to calculate bond energies. There's a series of steps. And you do need to take into consideration the big numbers in front of compounds. I'll show you an example in just a moment, which we can work through together. But calculate bond energies. First step, calculate the total energy needed to break bonds. Forgive me, the iPad pencil is working weird. Calculate the total energy needed to break bonds in the reactants. So always start with the reactants, and notice this bond breaking. The second step is to do the same thing, to calculate the total energy needed to make bonds, and this time in the products. The apostrophes mean the same as before, but I've made a few changes. So you calculate total energy needed to make bonds in the products. And then your final step, step 3, is to use the formula, which is energy change is equal to the total of your reactants. Let's abbreviate by writing energy. So energy change in the reactants, and you subtract the energy change of your products. But the great thing about this equation is there is no need for you to flip any signs or to do anything of that kind. All you need to do is plug in the values. So what we'll do is I'll work through an example, a worked example, a straightforward one. And the first example is a very famous, important process, the reason most of us will be alive right now in 2020, the Haber process. You will study this in year 11. And the Haber process is a very straightforward reaction, but has been very important for mankind and womankind. Nitrogen plus hydrogen make ammonia, NH3. I'm just balancing as I go along, but in fact, it's probably good exercise. The molecule on the right is called ammonia, those of you who are unaware. It's used in all kinds of different roles, but mainly as a fertilizer. Very important. This isn't balanced, so to balance it, we're going to go ahead and chuck a 2 in front of the NH3, which gives us 2 nitrogens on the left and 2 on the right. And then finally, 3 in front of H2 to give us 6 and 6. So that right there is essentially first part. We've got our balanced equation. Now, often you will be given, in the exam, you will be given one of these. This is a bond energy table. And the idea is they will give you values for each bond, and all you have to do is select the correct one and use it accordingly. Now, if I just move that out of the way, I will just read it out for argument's sake. So the values we've been given, or the ones that are interesting to us, NN bonds, they have an energy change, a bond energy of 945 kilojoules per mole. HH, 436. NH, 391. And for this reaction, these are the only ones we need. Now, before you get into this, you might find it actually quite useful to draw out your compounds, your equation. And what I mean by that is to draw out the atoms. So, for example, I know nitrogen is 2 nitrogen atoms, and they have a triple bond. If you didn't know that, all you have to do is look at your data sheet. And if I just bring that back in again, so there. The only bond with two ends is the bottom one, so you can safely assume that that is N2. Right, back out. And then we have hydrogen, H, H, but there are three of them. So I'm going to go ahead and draw three of them out just to help us visualize what's happening. And then we have NH3, and this is the way to do this is to realize N is in the middle, and it has three hydrogens around it. And then the big 2 in front, the coefficient, tells us there are two molecules of NH3. That should, I hope, help a lot of you to kind of visualize what's going on. What I'll do is I will give you 2 minutes to have a go using the values below, using these values here. See if you can calculate the total energy needed to break bonds in the reactants, total energy needed to make bonds in the product, and then to work out the energy change. And then I'll go through it anyway. But have a go. You have 2 minutes. You're looking at this, it's quite hopefully easy for us to work through, to work out energy. First thing first, we've got an N triple bond, which is equal to 945 kilojoules per mole. We're going to add on 3 HH bonds, so 3 times by 436. If we add that all together, the sum of this should add up to 2,253 kilojoules per mole. And actually, just to make things easy, I'm going to change that to yellow. That is our reactants, or those are our reactants altogether. Remember to multiply by 3 for the coefficient in front. And then on the right hand side, for the products, we need to count all of the bonds that we have. And if you notice, we have one NH bond here, another NH bond over here, another over here. So that's 3 NH bonds in one molecule. Because we have 2 molecules, we have altogether 6 NH bonds. So what I will do is, just to make it clear to you, I'm going to write that out, 6 times by NH. And then all we need to do is substitute in the value, 391. And that gives us a grand total of 2,346 kilojoules per mole. I'm going to assume that so far so good. And the last bit is to use our equation, step 3. Energy change is equal to reactants take away products. Let's go ahead and write that in. Energy change of our reaction is equal to reactants minus products. And that gives us 2253 take away 2346. And what that gives us overall is negative 93 kilojoules per mole. And that is our overall energy change. Final answer. And that's quite important because it tells us something about this reaction. No prizes, but you can write it. Student in the comments, excellent, is minus 93, so very well done. And just to kind of confirm something here, would this be exothermic or endothermic? Now, the answer lies in the symbol. And the symbol tells us this is negative, which means the reaction is releasing (93 kilojoules per mole of energy. Therefore, this is an exothermic reaction. You got that correct. Well done. Excellent work. What we'll do is to finish off today's session, lesson, I'll give you one more example, worked example, that you can work through. So example 2. In this example, we're going to do the combustion of methane, the burning of methane. CH4 plus O2 makes carbon dioxide and water. And to help you out, I'll balance this for you because for today's lesson, we're not worried about balancing. However, you will need to balance things in the real exam. So do be prepared to do that. You will need the values, the bond energies. I'll put them in a table here. While you wait, you might find it useful to draw each compound out underneath with the correct numbers. The bond energies you need for this reaction. You will need CH, OO, C double O, OH. There's the 4 bond energies. And the values we have. CH is 413 kilojoules per mole. C double bond O is 805. 498. And finally OH or HO 464. Again, I'll give you about 3 minutes to work through that. Methane, CH4. There are 4 CH bonds. I'm going to go ahead and write that underneath. 4 times CH. Oxygen gas is just O2, like that. There are 2 of them. Which means for our reactants, we've got to take into consideration 2 lots of OO. In the products, we have, here's a different color, a nice funky orange. CO2 looks like this, a weird looking molecule, but basically carbon with 2 oxygens and they're double bonds. So actually we can count here that there's 1 CO this way and there's 1 C double bond O that way, which means we have 2 times C double bond O. And then finally H2O looks like that, and that gives us 4 times by OH bonds. If you got that correct so far, well done. That's the first step. And then all you need to do is substitute in the values. So if we go ahead and substitute in the values, what we end up with is, let's get my pencil back. Here we are. 4 times by CH, which is 413, plus, and I'll put them in brackets, to make it quite clear. Oh. 2 times O2, which is 498. I'll calculate in just a second. And then we have, separately, 2 times 805 plus 4 times by 464. It's worthwhile showing all of your work because if you do make a mistake, remember there is something called error carried forward, which means you made a mistake, but that'll be carried forward in the exam. And that gives us, here we are, 2,648 on the reactant side. and 3,466 on the product side. The reactants and products are done. Final equation, energy change, equal to reactants minus the products, which gives us 2648, take away 3466, and that gives us an overall minus 818 kilojoules per mole. And once again, the negative sign tells us that this is going to be a exothermic reaction. And once again, well done, that's correct. That brings to an end this session on energetics. I've tried to cover everything in energy changes. You will need to go away and practice balancing equations. If you haven't, or if you missed the session last time, if you go to my channel, RMalik Science, there is a tutorial on there on how to balance equations, which you're welcome to use. And the questions that are in the description, download them, practice them. Maybe 20 minutes of questions, check your answers of the mark scheme, and then again. Okay. Until next time, next session we will move on to something new, and I will post it online in advance. And hopefully we won't have issues with technology. Thanks for tuning in. Like, subscribe, and share, and I'll see you next time.